Hello there. Okay, let's talk about the two fibrous proteins, collagen and elastin. So we talked about elastin. One of its main properties. It's very flexible, so it's going to be good for our skin, our blood vessels, the alveoli in our lungs as well. So let's just talk about what makes it flexible. So um, elastin is made up of many tropoelastins. I've just written it there. So this here is a tropoelastin. You can see it's a bit of like a wiggly little noodle shape, and it has the ability to wiggle up, and it can also straighten up. So you can imagine when it's relaxed, they take this shape, and when they get stretched, they can stretch out into their full length. And they work as one big unit, and we call this one big unit elastin. You can see they're held together. These little red marks here, they represent crosslinks. They're covalent bonds. So each of these tropoelastin molecules, they're not working by themselves. They're working as one big unit. So if this one here is getting stretched here, it's going to pull this one with it as well. And this is going to get stretched out as well. Same with this one. This is going to stretch out this one. And eventually, you're going to end up with something that looks like this on the right-hand side. And then when the skin or the blood vessel isn't stretched anymore, they return back to their original shape. So they have this ability to wiggle up, stretch out, and over again. Okay, the other structure is collagen. So you can see here there's 1, 2, 3 polypeptides that make up collagen. So we'd call those individual lines a polypeptide chain. If you put 3 of them together, you get a structure called collagen. And we say this shape is a triple helix, so they're twisted around each other. And they can go really close together, so it's a really compact structure, because within these chains, every third amino acid is something called glycine, which is a really small amino acid. It's small because it's got a small R group, so that these polypeptide chains can get really close together to make it a really compact structure. Again, a bit like the tropoelastin molecules, these collagen structures are going to work with each other. So you recognize these little dots I'm doing, these represent hydrogen bonds. So you can see that they're no longer just working by themselves, they're interacting with each other. This is a bit like how cellulose works as well. So by having more of them working together, their overall strength is going to increase, just like how rope works as well. So you can see here as well, there's little staggered ends here. Because these hydrogen bonds are taking place, it's going to bring these staggered ends close together, so we're going to get really long chains. So rather than just being one short chain like this here, now it's going to get longer. It's going to include this one here as well, and so on. And we call that, when it's one big long unit, we call it tropocollagen. So these little lines here, it's too hard to draw, but these represent the triple helixes. You can see, even though I've only drawn it as one line, I want to imagine that one line represents a triple helix. We've got 1, 2, so 1, 2, 3, 4, 5. I've drawn 6 triple helixes. So 6 sets of collagen, or because they're long, tropocollagen, and they're all hydrogen bonded together to make one big unit, and we call that unit a microfibril. So this is going to be really important for, it's going to be requiring lots of strength, and that's going to be important for tissues such as ligaments and tendons.